share. Okay, you should see something that says introduction.
We do.
No, I should see something. Okay. CLAMS, the quest for portability and audio. By the way, the hardware is not willing. There won't be any music. I can whistle Dixie, but that's about it. What is CLAMS? It stands for Command Line Algorithmic Music System. It's a fourth controlled synthesizer, and I'm going to be abbreviating that to synth for the rest of this. Save a couple of syllables there. For microcontrollers and single board computers. Here's some embedded audio terminology. MIDI stands for Musical Instrument Digital Interface, which is a protocol for controlling synths. PCM is pulse code modulation. That's digital audio streams of fixed width binary words. This is the most common digital audio format. DAC is a digital analog converter, and that converts a PCM stream from digital to analog. I2S or I2S is inter-integrated circuit sound. This is a serial protocol for transmitting stereo PCM, and DSP is digital signal processing. These are algorithms for manipulating PCM data. A typical digital performance setup consists of a controller, the keyboard, touchscreen, buttons, joysticks, drum pads, whatever, depends on the performer. A sequencer is a digital device that stores programs of MIDI information for playback. The actual sound is generated by the synth. There are effects, there's filters, echo, delay, reverb, chorus, flanger. This stuff evolved from what guitarists have been doing since the 60s. And of course, you need something to actually listen to the audio on. So there's headphones or speakers and usually a recorder. And these can all be in one box or in separate boxes. The CLAMS performance setup, you have a microcontroller or a single board computer, you have a serial terminal, you have a DAC amplifier, and then the usual headphones, speakers, and recorders. And you have a fourth and C code DSL, domain-specific language controller, the synth and the effects all run in the DSL. Previously on CLAMS. The original concept, early 2022, was to write a fourth for the Electrosmith Daisy Steed. This is a microcontroller board. It's actually designed for digital music. It has an ARM Cortex M7 microcontroller, 480 hertz. It has hardware floating point and DSP instructions. Has 64 megabytes of SD RAM, which is really useful for, like, you can put 10 minutes of audio in that. 8 megabytes of external flash. It has a built-in DAC, and so you actually have wired audio coming out of this thing. And it's 96 kilohertz, 24-bit audio, which is really overkill. For example, your ordinary CD is 44.1 kilohertz and 16 bits. And the native tools, there's a native C++ tool set and an Arduino tool set. These are $29.95 quantity one. And there are a number of package modules that contain this chip. It's very popular in the Eurorack synthesizer community. And the plan here was to do both the controller and the synth and port. Now, the revised concept, and this is the one I presented last year, was to do all of this on a Raspberry Pi Pico. That's a microcontroller board designed for general applications. So it's an ARM Cortex M0 Plus running at 133 megahertz. has a coprocessor for division, another one for interpolation, and another one for I/O. There's no floating point, there's no DSP, it only has 260 kilobytes of RAM and 2 megabytes of flash, has no audio hardware. You have to buy an expansion pack. I've got about 3 of those. But it's only $7. And again, the plan was to do both the controller and the synth and forth. Now, there were problems with this, with both of these. First of all, the lack of portability. You need to hand port the forth from one microcontroller to another. It's not as bad as it sounds. They're all ARM architectures. They all have GNU tools. But even so, if you do an assembly forth, you have to do a little bit of messing around. I had other desirable boards, the TNC 4.1 and the Raspberry Pi 02W and the ESP32s, the S3, which is Extensa architecture, and the C3 and the C6, which are RISC-V. And the TNC 4.1, this is another general purpose microcontroller. It has a 400 megahertz ARM Cortex M7. It does have hardware, floating point, and DSP. Does have it has a megabyte of RAM and almost 8 megabytes of flash. Doesn't have any audio hardware, but again, there's add-on modules you can buy. What it does have is a very comprehensive native audio library. It's a very popular microcontroller for audio applications. And these are 2960 quantity ones. And here, this is my favorite. This is the Raspberry Pi 02W. It's not a microcontroller. It's a single board control computer, but it's in a microcontroller sized board. It's a general application unit. It's quad core 64-bit ARM Cortex A53 running at 1 gigahertz. Hardware floating point, DSP instructions, 512 megabytes of RAM. Wow. There's no flash. It uses an SD card. There's no audio hardware, but again, you can buy add-on modules. It runs Linux, and they're $15, quantity one. This is cheaper than a TNC and way more powerful. And the second problem with the previous concepts was the only practical way of getting audio out of this thing is with an I2S DEC amplifier chain. There are other kinds of audio interfaces. There's class compliant USB audio and MIDI, Bluetooth audio and MIDI. The specifications for these are just way too complex for an easy implementation in Ford. They're very detailed. Things have to happen exactly at the right time. The effort to payoff ratio is enormous. And there are well-documented and tested C libraries for all of this stuff. It's just not something I wanted to spend months on. So the new design, we use Arduino or Linux for portability. The target microcontrollers all have Arduino support, and the Pi W has Linux support. I2S DAC audio is available on all the boards, either on board or in expansion hardware. Bluetooth audio is supported on all the boards that have Bluetooth hardware. USB MIDI is supported on all the boards. USB audio is currently supported on the TNC and the 02W, but the others are in alpha testing. And the second change is that I'm doing the synth. I found a synthesizer that will do everything I wanted and more. It's open. It's called Amy. It's open source on GitHub, and it's highly portable. It's written in C. It has an Arduino library. It has a a Linux version. It has a Python interface. It will handle both the and the I2S part, and it's a very capable synth. It would take me months to do what's in there. And it's the heart of something called the Tulip Creative Computer, which is it's a touchscreen. It's got an ESP32 in it, I think an S3, and it's got MicroPython. It's a very nice thing. It's $60 if you just want to pick one up. So finally, getting to the fourth part here, I'm using a fourth called C3. It's open source on GitHub by Christopher Curl. It's a stack-based, byte-coded fourth virtual machine written in C and C++. It runs natively on Windows, Mac, OS, and Linux. You just build it. And it runs on development boards. Currently, it's just configured for the Raspberry Pi Pico and the Teensy in Arduino. But it's easy to adapt to other boards. You just have to change one C file, a couple of header files. It's under active development. It's very well documented. Has a comprehensive README. It's got some extensions. It's an extended subset of ANS. Has 10 virtual registers, which are sort of like the registers in Stephen Pelk's advanced fourth virtual machine. Has 10 temporary words. It has inline words, which are like code words in regular fourth. It has lexicons, which are kind of like vocabularies, except they don't link back into the main dictionary. They're just little groups of words you can define for applications. And it's really easy to extend, add user-defined opcodes in C or presumably assembler. And it has a VI-inspired editor. And bonus fourth concept is C4. This one I think is going to be interesting to most of you fourth internals people. This is another one of Christopher Curl's fourth. It's open source on GitHub. It's inspired by Tachyon fourth and Color fourth. The Arduino support is in progress. It's very active. Has a very active next version branch. He's rewriting all the documentation. I don't know when he's going to be finished with this, but I really think the people who are interested in fourth internals should take a look at this one because it's really interesting. So the roadmap, these are tasks mostly in priority order. The first step is to integrate C3 and Amy on the Pico with an audio expansion board. This is essentially completing the second concept. I've got components working. C3 works on its own. Amy works on its own. It's just a matter of gluing them together. The main new code would be adding the C3 opcodes to talk to Amy. I'm not sure how many of those there are going to be. And then the second priority here is to make an album. I've kind of been putting off actually making music on these things. I've done a few little like 3-minute segments here and there, but I want to do something decent size with this. Adding the Amy synth has shortened the development time and greatly enlarged the kinds of music I'd be able to make with this. And this is going to be where I actually build the full DSL. And this is kind of a dog fooding process. And that will give me an idea of what kind of music I can make in fourth and actually define the language, grow the language at this point. And the third priority is to put this up on the Raspberry Pi RP2350W. I think this is really the sweet spot for CLAMS. The development cycle is a lot easier on Linux, and all the compilers are built in. Synth capacity is many times the capacity of a microcontroller. The Linux USB audio and MIDI are standard. Bluetooth audio and MIDI are standard in Linux. There is wireless hardware on this board. That's what the W in 2W stands for. I think Bluetooth audio is there. It's not a high priority for me because there are issues with latency in Bluetooth that probably will be exacerbated by Linux. There's many supporting audio software tools available. There's editors, recording software, and the total hardware cost for one of these is like $54.99. This is a kit that comes from Vilros. It has a Pi 02. It has a expander case that puts a couple more USB ports on it. It has a full-size HDMI adapter. It has an Ethernet port, and it's $54.99. And I've got the link there if you want to get one of these things for any use. It also comes with a power supply and a carrying bag, but the power supply and the case won't fit in the carrying bag. Longer range, TNC, do the TNC with the USB audio and the MIDI, do the DAISY with the DAISY hardware, and maybe the ESP32. I don't feel really compelled to do that because that's what's in the Tulip Creative Computer. And this is sort of the fourth equivalent of the Tulip Creative Computer without a touch screen. So. And that's about it. I've got a bunch of links here. I can leave these up if people want to write them down or answer questions, or just turn it over to the next speaker.
One quick question, if we have time for, but other than that, where you
I do have a question for you.
Make it fast.
Yeah.
Go ahead.
Did you consider like the 16 or 32 core XMOS microcontroller? Because I was looking at that for the same thing, music creation.
No.
So
Well,
it's
I've never heard of
XMOS.
them, so no.
No.
I'll put a link in the chat.
Okay, thanks.
You're welcome.
So I am done.
Is your email available?
Is there a what available?
Mom, I'm talking on my conference. What's your email, Mr. Borasky? Can you put it in the text possibly?
Oh yeah, okay. I can put my email in the chat.
All right, me too. All right, I'm Stephen Adels. All right, thank you.
All right. Oops. Move on. Put my slides up.